All right, let's get started with this seminar. My name is Duncan Keller. I'm a postdoc in the Clever Planets collaboration, and thank you all for being here today to hear Professor Oliver Shorttle's talk. Before I introduce Ollie, I have a few brief words to say on behalf of the Clever Planets collaboration. So the Clever Planets collaboration is a multi-institutional interdisciplinary initiative to unravel the conditions of planetary habitability in our solar system and beyond. Its lead institution is Rice University, and it's supported by NASA. It's one of the teams of the Nexus for Exoplanetary System Science Coordination Network under astrobiology. We also have a land acknowledgement. Our research at Rice University is pursued on the traditional lands of several native peoples, namely the Karankawas and the Sanas, as well as the Coahuiltecans, represented today by the Top Pilam Coahuiltecan Nation, and the Ishaks, represented today by the Atakapa Ishak Nation. We see it as a duty to acknowledge this historical aspect of our identity and to foster a beneficial environment for all communities, in particular, those who preceded us on this land. Now, about our speaker. Oliver Shorttle is an assistant professor jointly appointed in the Institute of Astronomy and Department of Earth Sciences at Cambridge University in the UK. Ollie's research covers a wide range of topics spanning geochemistry, petrology, planetary science, planetary habitability, remote sensing, and more. In 2015, Ollie was the Rice University Senior Peden Fellow, carrying on a long tradition of academic co-sponsorship between Rice and Cambridge. So with that, I'll turn it over to Ollie for the talk. If you have any questions during the talk, please feel free to type them in the Q&A section, and we'll have some time for questions and answers afterwards. And at the end, during that Q&A session, if you would like to raise your hand instead to ask a question using your microphone, you can do that. So with that, take it away, Ollie.
Great, thanks so much. Let me just share the screen. Does that look okay? Cool. Okay, well, thanks so much for inviting me to talk. I'm excited to present some of this work to you today. So yeah, I'm in Cambridge between the astronomy and earth science departments. My background is as an earth scientist, igneous geochemist, petrologist. But over the last few years, especially now, based between the astronomy and earth science departments, I've been investigating planetary habitability in the kind of broadest sense. In particular, kind of rooted in my background, thinking about the links between planetary interiors and their surface environments. And the topic I want to kind of speak to today is just to highlight kind of three bits of work we've been doing recently that speak to kind of the atmospheres that rocky planets might have. And I'm really excited about this kind of theme of our work in Cambridge because it connects between the earth sciences, both the present day and kind of going into deep time in earth history, planetary sciences in the solar system context, and then also exoplanetary sciences as well, where atmospheres will perhaps be one of our kind of key windows into exoplanetary geology or geological processes. So just to kind of step back before kind of focusing in on a couple of kind of case studies of what we're up to, the kind of big question we're really trying to understand is the processes understanding habitability, underpinning habitability on planets. This really ranges from work investigating formation processes, so how planets acquire the key ingredients for habitability, whether that be kind of chemical in origin or more process-based, how do they acquire the sort of geological processes that support and maintain habitability on kind of giga-year time scales. And that kind of leads on to thinking about early conditions, how a planetary climate's set up, and in particular, how is the prebiotic potential of a planet established, i.e. how are conditions created early in a planet's life that are amenable to abiogenesis occurring in the formation of biochemistry or emergence of biochemistry from geochemistry. And then finally, thinking about evolution of planets. And like I said, in particular, the role that a planet's interior might have in forcing the evolution of its surface environment on geological timescales. And whilst we're kind of doing work on a number of these aspects, and lucky to work with a fantastic range of collaborators, both in Cambridge and beyond. I think the topics we're going to focus on today are touching on these early conditions, climate and prebiotic potential, and the evolution of atmospheres. And just to kind of re-pitch this connection between geosciences and planetary and exoplanetary sciences, just to make a couple of kind of basic points about the challenges maybe we face as geologists focused on Earth in trying to understand Earth's own history. And a very simple one is the attrition of the rock record. And this is a figure from Shane and Peter's 2021 geology paper we had recently. And this one figure is showing sedimentary area over geological time. And what's evident from this is, whilst there's not exactly an exponential decay of rock availability going back in Earth history, it makes the very, the basic point that there's much less sedimentary rock as an archive of Earth's past present in deep time. That's obviously a catastrophic loss of rock at the beginning of the Phanerozoic, or going beyond deeper in time than the early Phanerozoic, kind of associated with the Great Unconformity. Relatively stable amounts of sedimentary rock, curiously, over much of the Proterozoic. But then we kind of hit the geological event horizon going into the Archean, beyond which there's little or no rock that remains, maybe only individual mineral phases. So much of Earth's own past is kind of lost to us from direct or certainly indirect study through the rock record. And then in a slightly broader context, there's limited diversity of planets in the solar system. The kind of parameter space explored by rocky planets in the solar system is diverse, comparing maybe Earth, Venus as maybe more geologically active planets, and Mars as certainly having been more geologically active in its past. But nonetheless, and as evidenced by exoplanets, that remains a relatively limited kind of parameter set over the whole range of possibilities of planetary types, masses, locations, variations in water to rock abundance, and indeed even the composition of the rocky silicate component of the planet itself. And so exoplanetary science offers a really exciting potential to explore rocky planets with some of these parameters tweaked, and offers us the possibility to then understand the outcomes in terms of the resultant planet of having tweaked those parameters, whatever they may be. So exoplanets will allow us to do some really exciting things as geoscientists. And I really like this cartoon from Chris Ballantyne's paper in 2002, just contrasting the early Earth with the present Earth. So a planet born in a magma-ocean state with potentially a massive atmosphere overlying a molten surface that somehow emerged hundreds of millions or several billion years later as the modern planet we know, with plate tectonics, continental crust, and a 1 bar atmosphere dominated by nitrogen. And we can only reach so far back in the rock record to understand this history, and almost by definition, some of those earliest processes, in particular the magma ocean processes, are going to be invisible to us, or are not going to be directly recorded in the rock record. So exoplanets potentially offer an opportunity to go and study planets that are in a perpetual magma ocean state, maybe because of their proximity to their host star. And that's what maybe is being emphasized in this diagram here, looking at a compilation of exoplanets plotted as a function of the insolation they're receiving, or insolation from their host star in units of Earth's insolation. So we're looking at planets that go from the same insolation as Earth to 10, 100, 1,000 times more light received from their host star, being received from their host star. And then planetary radius on the y-axis. So this kind of bottom quadrant down here, planets smaller than about 1.6 Earth radii that are receiving 10, 100, 1,000 times the installation of compared with the Earth. These are planets which on short period orbits are potentially extremely hot because of installation, if not also because of factors like their atmospheres, or indeed possibly also things like tidal heating that may be occurring in multi-planet systems. And this potentially gives us a sample of planets which, trapped in a permanent magma ocean state, allow us to explore a stage of Earth's history that was only transient and is mostly lost to us. Another aspect in which we can time travel with exoplanets is obviously thinking more broadly still, going to their actual birth environments, such as protoplanetary disks, with the beautiful ALMA image on the left of TW Hydra, 5 million years into its life, possibly forming planets, evidenced by the structure in the dust disk there. And at the other end of the spectrum, we've obviously got stars of different ages, and this image on the right is the so-called Methuselah star, that's very low metallicity and sort of within error of the age of the universe if you were to try and date it off the basis of the metallicity. So much more ancient stars and perhaps planetary systems to explore as well. So time is able to be explored at the present day through studying the nearby planets in the nearby galaxy. There's also aspects of sort of fundamental geology, fundamental to our understanding of Earth's own present habitability, which sort of remain debated and sort of difficult to resolve studying only Earth. And the one I'm sort of trying to hint at here with this really spectacular image of the Bengal fan is the carbon cycle, in particular the silicate weathering's role in stabilizing planetary climate, or more generally the processes whereby planetary climates may achieve a degree of homeostasis through chemical interactions between their ocean's atmosphere and rocks. And obviously this is something which the solar system planets have notably failed to do in the main. We have Venus with a massive CO2 dominated atmosphere and hundreds of Kelvin surface temperature, Mars, tenuous atmosphere and freezing surface temperature, and only Earth obviously having maintained this equitable conditions. So yeah, it's exciting to be able to, in the coming decades, investigate the efficacy of these basic planetary processes more generally. And that will speak profoundly to our own understanding of Earth, as well as planets beyond the solar system. But obviously, kind of coming from the earth sciences requires a bit of a sort of mental leap in terms of the actual kind of methodology we're going to use to investigate planets in these very different contexts. So, like I said, my background is doing igneous petrology, certainly during my PhD. And that top left image is a melt inclusion from Midfell eruption in Iceland, which we're continuing to study. I've studied and continue to do so for its potential insights into volatile inventory of Earth's deep interior. And we would go and collect samples like that and take them to instruments like you're seeing in the bottom left, which is a photo of the Edinburgh's Iron Probe, the 7F there. Moving beyond Earth, obviously the various missions to the solar system, planets and satellites have given us exceptional insight into geological processes taking place in the solar system. And I really love this image taken by Voyager 1 in 1979 of eruptions occurring on Io. As evidence that the solar system is geologically active in quite dramatic ways beyond Earth. And then obviously also the missions have even done in situ sampling, as we see in the Perseverance rover drilling into rocks on the surface of Mars today. So geology we can do in the solar system, even beyond Earth, is really exceptional and allows us to answer incredibly specific and detailed questions and throw an array of geochemical and even geophysical tools at them. Beyond the solar system, we're necessarily much more limited in the information we can contain. And one of the key, I guess, windows into geological processes is going to be the atmospheres of planets. And there's this really beautiful image from the space shuttle looking through the limb of Earth's atmosphere following the 1991 Pinatubo eruption, showing the aerosol layer that formed in the atmosphere. And it's to emphasize that planetary atmospheres are being, certainly in short time scales, directly perturbed by the geological processes taking place on their surface. And that perturbance of the atmosphere by geology is not only a transient, short-lived event, as with the Pinatubo eruption cooling the surface of the Earth by sort of 0.5 degree on average over a couple of years, but also a long-term interaction whereby the atmosphere itself is built by geological processes. And so that's really the context of the talk in terms of, I want to understand the geochemical, geophysical potentially biological processes taking place on a planet, but need to recognize that doing that is going to be through a rather different kind of window than I would typically use in asking these questions of the Earth. So we kind of need to view these processes through atmospheres. And whilst that spectacular space shuttle image showed really nicely how atmospheres are perturbed by volcanism in that case, the kind of observations we're going to get of exoplanets are obviously rather different. And there's a really nice image here, which is sort of obviously of a solar system, in this case, the transit of Venus in 2004, but perhaps which is philosophically a bit more like kind of an exoplanet observation. So in this sense, we're seeing a ring of light around Venus as it's on its way over, beginning its ingress into the stellar disk. And that ring of light was observed in 1760s and used to infer the presence of an atmosphere around Venus. In fact, there was refraction in the upper layers of the atmosphere of the sun's light. And I feel that's kind of an observation which sort of in its first order nature is perhaps a bit more similar to exoplanet observations, albeit obviously it's still relying on a degree of resolution that is not yet attainable for observing exoplanets. So in this talk, I want to kind of view geology through atmospheres, and I'm going to kind of touch briefly on three topics: impact atmospheres to begin with, volcanic atmospheres, and then very, very quickly, hopefully if there's time, comment on Venus-like atmospheres. I'm sorry, I'm going to be dancing over each of these topics, but they each relate to papers that either kind of are out, nearly out, or on archive. You should be able to find more details of. Okay, to begin with, I want to think about impact atmospheres, and this is work that's been led by Johnny Itkowitz in Cambridge, a graduate student I work with, and should be hopefully appearing on archive in the next couple of days. And with this work, we want to ask, we've been asking, what type of atmospheres do impacts create? And in particular, what are the implications of these atmospheres for planetary climate and prebiotic chemistry, recognizing that these impact events are sort of the late stages of planet formation. They're sort of happening during the late accretion stage, and so potentially set the initial conditions for a temperate planet, or a planet that may be temperate. So it's initial chemical environment being set by the outcome of these impacts. And the solar system obviously gives us a useful insight into the relevance of thinking about impacts or kind of late accretion as a force that's sculpting planetary surfaces. On the left, it's kind of an image of the moon, looking at Moltke crater, about 6.5 kilometers across, the one in the center of the image there. And the moon is obviously littered with craters, as we see looking up into the night sky, and provides a fantastic archive of the bombardment history of the inner solar system following protoplanetary disk dispersal. And yeah, so we know that the Earth was bombarded by material following the majority of its assembly having occurred. And on the right, we see kind of larger scale enigmatic features that potentially attributable to very large impacts, like the hemispherical dichotomy on Mars, the southern highlands, and the smooth plains of the northern hemisphere. So, you know, the solar system had an epoch of significant impacts in its history, which could have influenced the Earth's own early atmospheric chemistry. Looking beyond the solar system, there's fantastic evidence. Again, we're looking at an ALMA image here of a Fomalhaut system 25 light years away, of debris being present following protoplanetary disk dispersal in these systems. There's a star in the center, and this is a ring of debris. And the geometry of this ring, in fact, has been argued to evidence the presence of planets that are actually shepherding the dust that's glowing in the infrared here, shepherding the dust into this narrow ring. So not only is this a system that has debris present, it also has planets present that may be being influenced by some of the larger bodies that are colliding and grinding down to produce that debris. And kind of from a more statistical perspective, there's a nice review by Mark Wyatt in 2008 that shows estimates of disk mass as a function of the system age. This population at the top are the protoplanetary disk hosting objects, and this population down here are the ones hosting debris disks. And you can see the debris disks extend out. There's objects with debris disks, you know, from 10 to 1,000 million years old. And the mass of the dust mass being observed is anywhere between, you know, close to an Earth mass down to 1% of an Earth mass. And that observed dust is sort of, you know, is the product of larger material grinding down. So you could imagine there's a larger reservoir of rocky material in these systems that underpins these observations of fine millimeter-sized dust particles. The point being that there's abundant astrophysical evidence for debris being present following planet formation. So not only a kind of post-formation impacts going to be relevant to understanding solar system planet history, but also exoplanet history as well, potentially. And then finally for Earth, just to kind of put a geochemical observation in to contextualize thinking about late accretion of material to the Earth, there's the kind of, you know, the well-known observation of the abundance of highly hydrophile elements, these looking at rhenium to palladium on the x-axis there, their abundance in Earth's mantle, shown here relative to CI chondrites. And the primitive upper mantle is shown, plotted here, to have relatively, you know, essentially chondritic relative abundances of these highly hydrophile elements. And in abundance is much higher than would be predicted from partitioning of those elements between silicate and metal phases. And that's what these other lines show, are predictions if highly hydrophile element abundances in Earth's mantle were set by core formation. They should be much less abundant than they're observed to be. So this evidence is potentially some late delivery of material to Earth's mantle. And potentially that was an object that could have been large enough to also perturb the surface environment when that impact occurred. And so the kind of one of the key processes we're interested in thinking about here, and I'm certainly not the first to do this, many people have thought about impacts, Kevin Zarnley published on it, is thinking about the interaction between water and reduced phases in the impactors like metallic iron. The result of that interaction could be the oxidation of the iron and the production of H2 gas. And that would happen because potentially the impactor is differentiated and so has a large metallic iron core, which could directly interact with surface reservoirs on the planet. And the production of large reservoirs of reducing gases at the surface of a planet is potentially significant in the context of prebiotic chemistry. So the kind of famous Miller-Urey experiment, and we're seeing the kind of Miller-Urey apparatus in this diagram on the right. This is the spark chamber would have been up here, water being supplied from a chamber down here, organic molecules condensed out in the cold trap at the bottom there. You know, this experiment was run with a very reducing atmosphere. So given at the top here, a kind of methane, ammonia, H2 mixture. And that kind of gas mixture is quite different to what you'd presume you know, an Earth-like planet might have of it as its sort of primary atmosphere as a product of, say, magma ocean or volcanic degassing, in which you might expect to be a more water CO2 dominated atmosphere, given how oxidizing Earth's present day mantle is. But what giant impacts can do by virtue of that reducing capacity they bring, or big impacts can do by virtue of that reducing capacity they bring to a planet's surface, is potentially produce a lot of water by hydrogen, dihydrogen, by reducing water. And then also, in addition to prebiotic chemistry, there's potentially also a kind of climate significance to the production of large quantities of H2 gas at the surface of a planet. So this is a graph from Rabia Humbert's paper in 2011. And what we're seeing is the surface pressure of H2 gas required to maintain a 280 Kelvin surface temperature. And this dashed line is for a G star. So if we imagine Earth here at 1 AU, then it kind of actually lies off the extension of the line. But we're seeing that in order to maintain kind of you know, a habitable surface temperature at Earth's surface, it requires less than a bar of H2 gas in these calculations. And indeed, if you reduced all the oceans, you'd have you know, well over 100 bar of H2 gas at the surface of the Earth. So that would, by inference, put Earth into a kind of runaway greenhouse, or it would heat up the surface of the planet extensively, at least for a period of time, if that was the case. So, and that might actually be, whilst we wouldn't necessarily want hundreds of bar of H2, some amount of H2 present on the early Earth that stuck around for a reasonable amount of time could actually be an important contributor to maintaining habitability in the face of a faint young sun. So Johnny's work has been to investigate these impact processes and look at the efficiency of H2 gas production at the surface of planets as a result of large impacts via this reaction, the reduction of water by metallic ion to produce iron oxide and H2 gas. And this is kind of just a schematic of the setup. We have a planet with a surface ocean to begin with, pre-impact, the impactor hits, and then something's going to happen with the iron. Some of it may be used up in reducing that water. And our fiducial result is going to be the scenario where the impactor hits, and we're looking at different impactor masses on the x-axis here. The impactor hits the planet, and all the iron in the impactor goes into the atmosphere, which is now has got kind of supercritical water in it, and reduces that water to produce H2 gas. And we're just counting the H2 gas. These orange symbols are column density in moles per centimeter square of H2 gas. And just for context, I haven't put it on exactly, but that's kind of looking at tens of bars of H2 equivalent up on the right-hand side here. So producing very large quantities of H2 gas, increasing with impactor mass, because the bigger the impactor, the more iron is delivered. The square symbols are showing the same results from Kevin Zame's 2020 paper, just showing that this kind of fiducial model represents, or something kind of close to the scenario Kevin was modeling in that 2020 work. So what Johnny's done is consider some additional processes, and there's two in particular that are important to think about here. One of which is the fate of the iron of the impactor, and that is whether all that iron of the given impactor actually ends up in the Earth system, or whether it ends up leaving it. And potentially also there's a question of if it is in the Earth system, where it is, whether it's in the mantle or whether it's kind of in the surface. And then the second process is that these big impacts generate melting. I should have said that we're looking at impactors 0.2 to 2 times 10 to the 22 kilograms. So these are impactors sort of 1% the mass of the Earth and below, roughly, maybe 10 times smaller than the kind of moon forming impact, if that was a sort of canonical kind of Mars size impactor. So we're looking at the fate of the iron and the presence of a melt phase, and what is a melt phase going to do to the resultant chemistry of the atmosphere, given there will be chemical interaction between the melt phase and the gas phase. And to do this work, we've worked closely with Robert Citron and Sarah Stewart, who kind of at the same time we're doing new SPH simulations of impacts looking at the fate of iron. And that's just kind of a snapshot of their paper here, which is up on archive and submitted to Planetary Science Journal. So we worked with Robert and Sarah on this, taking their results and then adding them into a kind of chemical petrological model that we developed. So the first kind of additional process you want to think about is the metal loss, like the fate of the metal, what happens to it. And we're going to look at it under 3 scenarios, depending on the impact angle. So 30 degrees is a relatively kind of head-on impact, over to sort of 60 degrees where you've got more oblique impact. And what we're looking at is the ion distribution in these graphs as a function of impact and mass again. And these are just 10 to the 22 kilogram kind of units. So we see that for a relatively head-on impact, almost all the iron of the impactor core ends up in the planet, ends up in the interior of the planet. As the impact becomes more oblique, less ends up in the interior, more ends up in the atmosphere, so kind of in the surface reservoir, probably sort of speaking more generically. And then a significant fraction starts to not be accreted at all and actually just leaves the system, so isn't able to participate in the chemistry, driving reduction of water and production of H2 gas. And that trend then becomes kind of more extreme as the impact becomes more oblique, where now it actually crosses over and most of the impactor core isn't accreted. So we're going to primarily look at, in subsequent plots, we're going to look at a case where we've got a 45-degree impact angle as a sort of typical impact case. And this is one where, considering ion distribution is significant compared with assuming it all goes into the atmosphere. And this is the result. So the dotted line is the fiducial scenario of all the impactors iron going to the atmosphere and able to perform reduction and producing an H2 gas. By considering the distribution of iron, we get this solid line down here. So we get about an order of magnitude decrease in the amount of hydrogen gas produced in the atmosphere by accounting for the distribution of iron in the system. But this is still a relatively simple model, because this is now just the only iron that's allowed to do reduction in this model is iron that ends up in the surface environment. So that doesn't go into the mantle and doesn't escape the system altogether. The second process, which is important to think about, is the generation of melts. And this is going to end up modulating what we think the significance of iron distribution is, just to kind of preempt the conclusion. So Robert and Sarah's calculations, SPH simulations, also provided fantastic estimates of the amount of melting that was occurring in these impacts. And that's what's plotted in this graph here. The melt mass is a function of impactor mass. Again, with a kind of handful of parameters being played with the velocity of the impactor and the impact angle. The kind of key point is just that melt mass is increasing with impactor mass is the key thing. And we can incorporate that into the model and look at the effects of melt generation by adding in an additional step whereby the atmosphere then re-equilibrates its composition with the underlying melt pool. And that requires a redox equilibration and indeed a solubility equilibration between the overlying gas phase and the melt pool, the kind of magma ocean or magma pond that's created by the impact. So these squares are kind of roughly the fiducial model from Kevin Zarnley's work. And we've got two scenarios of what happens purely considering the effect of melt generation. These curves labeled P and B. And these represent two scenarios for how oxidizing the melt pool is basically. In one case, it's a peridotitic liquid, which is relatively reducing. In the other case, it's a basaltic liquid, which is relatively oxidizing. You can see that the peridotitic liquid recovers essentially the fiducial scenario. It starts off about as oxidized as the atmosphere is with the H2 gas in it. So there's very little redox exchange, whereas the basaltic liquid, by being more oxidized than the atmosphere, consumes H2 gas from the atmosphere to produce water, and so a slightly less massive H2 atmosphere is produced. Oops. So what we want to do is combine these two scenarios, because we know that if an impact's happening, it's both going to cause melting at the surface and going to distribute iron both out of the system into the interior and to the surface. So we need to kind of put everything together to really understand what the outcome is going to be in terms of the sort of initial planetary atmosphere produced by a large impact event. And we kind of carry forward two uncertainties, one uncertainty, which is what the fate of the iron in the interior of the planet. And we're going to show results for each case, one of which is where the iron goes into the interior, but remains well mixed with the melt phase. That's this scenario on the left. And a second scenario where the iron goes into the interior, but then segregates, and so isn't able to influence the chemistry of the melt, and thereby influence the chemistry of the atmosphere the melt is equilibrating with. Okay, so for the start on the left-hand side where the iron stays in the melt, in that scenario, we obtain a result very similar to the one we just looked at, in fact. So we get a scenario, but in both the peridotite and basaltic melt case, where the amount of H2 in the atmosphere is very similar to the fiducial scenario. And that's simply because all of the iron is available to react with the atmosphere, even if it's doing it via reduction of the melt pool, and then subsequently by atmosphere magma ocean interaction. In the second case, where the iron falls out of the melt and is lost to the interior of the planet, then we see very significant decreases in the abundance of H2 in the planetary atmosphere compared with the fiducial case. And then it becomes important how oxidizing the planet's mantle is, basically, to start with, whether it's more like a modern Earth-like peridotitic mantle, or whether it's like an Earth-like basalt, or anywhere in between, as a function of how it's melted and what its initial composition was. So just to kind of highlight that we're kind of taking next steps to try and understand in more detail where the iron ends up in the interior, because Johnny's first piece of work really emphasized the importance of constraining that parameter for understanding these post-impact atmospheres. To do that, we've collaborated with some colleagues in Imperial to use the ISAIL code, which offers some advantages over a typical kind of SPH simulation in that it has a strength model. So the iron that accretes to the planet doesn't all end up falling to the core, but actually is distributed through the mantle. And that's what we can see in this kind of preliminary simulation shown kind of in this video, that the yellow of the core, some of it stays in the mantle, some of it sinks to the core mantle boundary and maybe is not accessible for interacting with the atmosphere of the planet. So that's where we're going with this work. So just to sum up this kind of first part, we've asked the question, what type of atmospheres do impacts create? They create reducing atmospheres, but what we've been able to show is that the distribution of iron matters, of the impactor iron matters a lot for how reducing that atmosphere is. And because the distribution matters, you need to worry about melting, because melting is the process that allows any iron distributed to the planet's interior to re-interact with the atmosphere and still contribute its reducing power. So overall, we're seeing by considering these processes, we're going to get less reducing post-impact atmospheres than sort of a fiducial scenario where all the impactor ions made available for reduction. But we're still working on exactly how that ion distribution operates, and so how reducing these early planetary atmospheres can be, with the associated implications for running prebiotic chemistry on the early Earth, or stabilizing planetary climates in the face of kind of faint young sun paradoxes. The second project I want to kind of quickly touch upon is volcanic atmospheres, building atmospheres now by volcanism. So this is kind of taking a step from Johnny's work, which I guess sets initial conditions in the late accretion stage, to looking at the growth of atmospheres over kind of billion-year timescales by volcanism. And this is work that Pip Liggins has carried out in Earth Sciences in Cambridge, grad student I've been working with. And what we've asked is just a kind of really simple question is, what does a purely volcanic atmosphere look like? As sort of an n-member case that we could then build other geological processes onto. And in particular, what information does this contain about a planet's interior? So are we going to be able to learn about planetary interiors by studying their atmospheres in the simplest case of the atmosphere having been built just by volcanism, in a kind of closed box scenario? I'm just going to run through these cartoons quickly, but it's just to kind of emphasize there are a lot of processes that affect planetary atmospheres on the modern Earth, or Earth-like planets that have liquid water at their surface. Degassing is obviously, of the solid Earth, is only one process that takes place. Obviously, the atmosphere is then heavily modulated by low temperature processes at the surface of the Earth, like subaerial weathering and mineral precipitation from water. So understanding the formation of an atmosphere in an Earth-like planet be rather more complex than simply running a volcanic degassing code. Similarly, in an exoplanet context, there may well be planets which have vast water envelopes. And here there may be, there's questions over the degree of interaction between the interior and the exterior environment, and whether or not volcanic degassing is even contributing to the evolution of these planets, given the high pressures at which the interface between the rock and the ocean may be at, and whether or not any gases could escape a magma, even if it found its way to the surface. Finally, the kind of most relevant planets to think about for simple kind of build up a volcanic atmosphere are kind of going to be Venus-like planets. So planets that are hot, maybe have a thick lithosphere, but in which volcanism is still occurring or has occurred extensively over the planet's history. But there's perhaps more in a regime where there's release of volatiles to the atmosphere, and by virtue of the absence of liquid water at the surface, there's fewer routes to bring some of those volatile species back out of the atmosphere into the rock record again. So it could be considered or modeled as a kind of volcanic buildup of an atmosphere, modulo processes like escape. So again, coming back to this diagram, looking at the exoplanet catalogue, planetary radius and insolation flux, we're thinking about these kind of volcanic atmospheres perhaps being most relevant to planets in this lower quadrant, planets that maybe lost their atmosphere early in history by photoevaporation, and are rocky. So Pip's work has involved building this fantastic volcanic degassing code that's available on GitHub called EVO. And in this piece of work has coupled EVO to a kind of a simple model looking at planetary evolution. So melting of a mantle, bringing of magmas to the surface and they're degassing into an atmosphere. And just kind of running that simple process over 100 million years, a billion years, and looking at the atmosphere that builds up, considering things like the pressure at the surface that obviously inhibits volcanic degassing progressively and changes the speciation of volcanic gases leaving a magma, but also the changing volatile content of the interior of the planet as it progressively is processed through melting regions. Just very quickly, the code considers gas chemistry in carbon, hydrogen, nitrogen, oxygen, sulfur system, homogeneous equilibria between those species in the gas phase, coupled to the melt through iron redox chemistry, and obviously also solubility laws, some of which are of this form, some of which are not of this form. This is kind of just illustrative, but obviously accounting for the fact that gases are going to be dissolved in the silicate liquid. And the primary kind of planetary interior variable we're going to think about is FO2, how oxidizing the mantle is, shown here for bodies in the solar system on the iron Wüstite scale, delta iron Wüstite. So Earth is going to be over here somewhere on the right, kind of 3 to 5 delta iron Wüstite, 3 to 5 plus 3 to 5. The Moon significantly more reducing. Mars is kind of intermediate, and then some of the smaller bodies like Vesta and Great Parent Body kind of similarly reducing to the Moon. So we know within the solar system there's this diversity of planetary mantle FO2s, how oxidizing they are. We might expect this to be similarly true in exoplanetary systems, or indeed it would be very interesting to discover whether exoplanets have a diversity of mantle FO2s or not. So this is going to be, just in this brief talk, it's going to be the key variable we look at. And first of all, let's look at the physical properties of atmospheres that are created after 1 billion years of volcanic degassing on an Earth-like planet. And the only parameter away from Earth-like that we've changed here in these figures is just the mantle FO2. Is it a lot more, is it about as oxidizing as Earth's mantle, kind of over on the right here, or is it a lot more reducing, kind of closer to sort of the lunar mantle FO2? And looking at the physical properties of the atmosphere, we see the scale height increases as the atmosphere becomes more reducing. And the scale height, obviously, of the atmosphere also inflates as the atmospheres get hotter. We're just showing results for an 800 Kelvin to a 2000 Kelvin atmosphere here. And this kind of expansion of the atmosphere as the FO2, the mantle FO2 decreases, simply reflects the changing mean molecular weight of the atmosphere. So as we go from right to left, we're looking at more reducing atmospheres again. And those reducing atmospheres have a lower mean molecular weight because we're looking now at molecules that don't have an oxygen on them, basically. So take the oxygen away and you've got a lower mean molecular weight. And that's kind of what we're seeing kind of right to left in this diagram. There's also some interesting kind of chemical properties of these atmospheres on planets after 1 billion years of volcanic degassing. Looking at the carbon species here, we see reducing planetary mantles produce volcanic atmospheres dominated by methane. I should say now we're looking at an 800 Kelvin atmosphere. So this is kind of like a sort of Venus-like case for a kind of warm exoplanet atmosphere produced by 1 billion years of volcanic degassing. So here it's got, on the left is methane dominated, on the far right, where it's oxidizing, it's CO2 dominated, and in the middle, there's this regime where there's both relatively high abundances of methane and CO2. And also CO becomes significant in the intermediate regime. If we look at hydrogen species, see large amounts of H2 gas at low FO2, and then that drops off in the oxidizing atmospheres. Sulfur species really only become abundant, OCS and SO2 only become abundant kind of over in the oxidizing side. And then finally ammonia, again, disappears off when you get into these oxidizing regimes above iron Wüstite +3. So we can see this kind of interesting chemical structure to atmospheres that emerge from volcanic degassing that hints at kind of a broad classification of atmospheres into these FO2 regimes from key chemical kind of tracer species like methane, sulfur dioxide, and CO2. So on the left, we can see there's these kind of reduced planetary atmospheres that are formed that are rich in methane and hydrogen. In the middle, we've got an intermediate case where CO2 also becomes significant, essentially. And then on the right-hand side, the methane disappears, becomes CO2 dominated, and we start seeing species like SO2 present in the atmosphere. So Pip's work is just probably going to come out shortly and has been looking at what these kind of pure volcanic atmospheres look like. And we've seen that both the physical and chemical properties of the atmosphere depend on mantle FO2, subject to the evolutionary history of the planet for warm planets. So what I've not shown are any results looking at escape and looking at chemical kinetics in the atmosphere. That's all stuff that we're working on. But that first push, putting the model together and building these kind of simple closed box volcanic atmospheres gives us this insight into the kind of end-member case of volcanically produced atmospheres. Finally, and just kind of following on from that, I want to just ask this question: how can we identify an exovenus, which is kind of like asking how can we identify these warm, volcanically influenced planetary atmospheres? And this is work that Sean Jordan in Cambridge has been doing. And what Sean's done is built upon the excellent work of Paul Rimmer in putting together this self-consistent model for the atmospheric chemistry of Venus. And that's what we're seeing, this beautiful kind of illustration up here of some aspects of the chemical network Paul has built for understanding Venus's atmosphere. And there's a lot of detail here that I don't really want to get into, and certainly don't have time to get into. But the key point, or the key challenge in the context of studying exovenuses, is that the cloud layer, the sulfuric acid cloud layer, is going to limit transit observations in all likelihood to this kind of upper region of the atmosphere above the clouds, which is strongly influenced by photochemistry. So what it means is to kind of observe an exovenus, we need to understand what this kind of upper atmosphere, photochemically influenced region of the atmosphere looks like for Venus-like planets. So just to kind of look really superficially at the results from Sean's work, which has been really excellent, so I'm sorry I'm not able to do it justice here. This black line is the result of this self-consistent Venus model applied to Venus. And the gray symbols are data here, kind of trying to indicate that for OCS, estimates of OCS in Venus's atmosphere, the model can kind of roughly reproduce these within about an order of magnitude. And the key thing that we're seeing is that from within the cloud layer, essentially, which starts just below 1 bar, extends maybe to 10 to the minus 2 bar, we're seeing very strong depletion, photochemical depletion of OCS in Venus's atmosphere. That means that the below cloud mixing ratio of OCS, which might in principle be detectable on an exoplanet, OCS is spectrally active, is orders of magnitude depleted in the region where we'd actually be able to observe in an exovenus atmosphere by transit spectroscopy. However, what Sean's done is look at this for a variety of different cases by putting a Venus-like planet with a Venus-like installation around these different stars. We're going from, so Earth's obviously orbiting a G-type star, going down in the colors from blue to red to progressively cooler stars. And you can see that in these models, the OCS mixing ratio remains high when you start getting to cool K dwarfs or into M dwarfs. And that reflects the different UV flux that's driving photochemistry in these atmospheres. So OCS survives to higher altitude in the atmospheres of Venus-like planets around these cooler stars. It's not photochemically destroyed. Another way of looking at that is if we directly plot the column density of OCS above 70 kilometers altitude as a function of host star temperature, we see on the right, we've got the kind of Venus case where there's strong photochemical depletion of OCS. Once we get below about 4,500 Kelvin, OCS survives, the mixing ratio in the lower atmosphere survives through the clouds into the upper atmosphere without photochemical destruction. And that's really significant. It means that OCS may well be a good fingerprint for a Venus-like planet if we're looking around cool stars, where it's going to remain a challenging fingerprint if we were to look for a G-type star. So in the context of discoveries or observations that might be focused around, looking at planets around low mass stars, this is kind of good news for discovering Venuses and distinguishing them from Earths. So to answer that question just very briefly, how might we spot an exovenus? Well, there's prospects of using trace sulfur species around cool stars. So that's the end of my talk. I kind of summed up as we went along, but just to kind of highlight that we're kind of working on various aspects of these kind of interior surface interactions in the context of planetary habitability, and I'm lucky to work with a fantastic range of people, and put some of the names up here: Johnny, Sean, and Pip, who led the work that I presented, and then collaborators in Cambridge and beyond. Thank you very much for listening.
Thanks a lot, Ali. We can get started with some questions. We have a question in the chat from Michael Way, who asks, regarding volcanic outgassed atmospheres, how do your results quantitatively compare to that of Gaillard and Scalé, Bauer et al., etc.? A lot of work in this domain in recent years.
Yep, yeah, so that's a good question. So I'm not going to be able to give a quantitative answer to the question of quantitative comparison off the top of my head. But what I will say is, like, so there's definitely, first order similarities, because we're ultimately all modeling volcanic degassing, which is obviously rooted in experimental petrology. And it's the same or similar experimental petrology that's the foundation of setting up those models and those parameterizations for solubility laws and speciation of gas species. Where there are differences, so one difference in the work that Pip's done has been considering the thermochemistry of the atmosphere at the surface temperature of the planet. So volcanic degassing occurs at the temperature of a magma. That gas then goes into the atmosphere, and the surface conditions on the planet may be a different temperature to the magmatic temperature. And so kind of trivially, thermochemistry, if the gas maintains thermochemical equilibrium, it's going to relax its composition or its chemistry to that of the surface. And so that's a process which hasn't always been included in some of the models. Pip's follow-up piece of work has been looking at the timescales for that relaxation. But that's one way in which it differs. And there's also kind of more sort of technical differences in the treatment of sulfur in particular, because it's got a rich, complex and rich chemistry and behavior in magmatic systems, which can lead to some differences between models, and that's also a source of difference. But yeah, the paper I think will be coming out soon or appear on archive. So for a more direct comparison, I'd point you there. But thanks for the question.
I have a question about the iron impactors. I was quite interested because you're talking about the potential formation of FeO, right, which is wustite in that reaction. And the melting behavior of that planet's mantle is going to be in some ways influenced by the ratio of periclase to wustite that's in that assemblage. Would it be fair to say that there's probably a comparatively small effect on the chemistry of the mantle in terms of how much FeO gets in there if you have one of these more direct impacts where the FeO stays inside the planet versus the effect in the atmosphere? Do you expect a larger atmospheric effect than a mantle chemistry effect from that process?
Yeah, I think this is, so I think so Johnny's paper was kind of focused on modeling the Earth, so sort of modeling the specific case of the Earth, I guess, in which case we, to some extent, we kind of lose a free parameter in terms of the chemistry of the interior. But we're really interested in extending these calculations for exoplanets, where the chemistry of the interior could be really diverse, and with the result that its influence post-impact, the influence of the mantle, the melted mantle on the atmosphere post-impact could be really different to what we expect for the Earth case. In particular, like you're suggesting, you could imagine scenarios where there's there's way more reducing power in the mantle than there is in the impactor, and the result of the impact is actually it's primarily just to allow the interior to re-interact with the surface environment, and kind of assert itself, and the reducing power of the impact is not terribly significant. So yeah, I think it will vary, and actually also just, yeah, maybe like you're saying, the volume of melt produced will also just be a basic physical parameter which will be sensitive to the solidus and productivity function of the target mantle. So there's going to be a lot of kind of diversity of outcomes, I think, if and when we extend to thinking about the exoplanet case, and how making those predictions of what an exoplanet atmosphere that we think is the result of an impact should look like.
Maxime?
Yeah, I had a question coming back to your outgassing model. I just wanted to make sure I'm envisioning it correctly. So you first evaluate how much volatile go during the melting into the melt. It's partition from the solid to the melt, and then this melt is reaching the surface, and there you calculate the equilibrium between the melt and the atmosphere. Is it how you're doing?
Yeah, sorry, I really ran through that explanation. So yeah, it's good to be able to clarify. Yeah, so what we do is we have like an initial melting step, which is very simple. We just have a mantle that's kind of like a box. So we just partition elements into the melt phase as a function of their partition coefficient, or with a little bit more sophistication in the case of carbon, if there's a graphite present or whatever. That melt then moves to low pressure, moves to the surface with some efficiency factor, which I think it's not probably super relevant for the outcome of the calculation. At the surface, that gas then degasses to 1 bar, or whatever pressure is at the surface at that time, and the calculations start from a sort of arbitrarily low pressure. So the atmosphere is totally built by volcanism rather than having any kind of initial condition that's relevant for its eventual composition. So the magma just degasses at that pressure. So the gas phase is built up until it's in equilibrium with the melt at that pressure and temperature. So it's like a kind of batch degassing step. And then that gas at magmatic temperature is put into the atmosphere. And the atmosphere itself may then be at a lower temperature than magmatic temperature, roughly 1500 Kelvin. So maybe the atmosphere is 800 Kelvin, at which point we now have got a new atmosphere kind of pool, which adjusts its chemistry in response to this new input. And in the models I showed, at least, that adjustment is instantaneous. We just allow the thermochemistry to adjust the composition of the chemistry of the atmosphere instantaneously. So the composition is set by the volcanism, and then the chemistry is set by low temperature, quote unquote low temperature, like 800 Kelvin, or equilibrium. Yeah.
Okay, yeah, I guess what I was trying to, so that's kind of really helpful here. What I was trying to understand was the particular case of sulfur, the fact that you have sulfur mostly at oxidized conditions, and I was trying to see where you might have bottleneck controlling whether or not sulfur is going to be outgassed, because I guess sulfur has there's a strong influence of FO2 on its solubility, right? So I guess that must be what is directing what is governing this trend.
Yeah. So the behavior of, well, the significance of FO2 was really strong in the case of sulfur in switching. What I didn't plot was H2S, but what in effect was happening was that an H2S abundance was decreasing, and there was a massive increase in SO2. And so we're changing both the amount of sulfur that's coming out of the magmas and the speciation of the gas. So that wasn't obvious from the plots. All we saw was that SO2 suddenly appeared, but both things are changing at once because of the combined effect of FO2 on gas phase speciation and melt phase solubility. Yeah.
Okay, thanks.
We have a raised hand from Vladimir Arapetian, so I'm going to allow them to talk and ask their question. You should be unmuted now.
Can you hear me? Hello. Yes. Hello.
Yes. Hello.
Yes, I have one. Yeah, I have one comment and one question. So the comment is about the atmospheric escape. So the fractionation of oxygen can play a very important role in atmospheric redox. So the point is that when XUV flux from the star is less than about 60 times the solar of the current solar flux, then the efficient ionization of oxygen can create O+, and the ion escape can contribute to the escape of oxygen from the atmosphere. So that's the one thing that normally when people talk about atmospheric escape, they talk about the evaporation and the bulk of the, but for the evaporation, you need a very high XUV fluxes, about like greater than 60 times. But if it's less than 60 times, then, the O+ escapes exactly the way it escapes from our Earth, every single second, and actually O+ escapes 3 times as much as the H+. So that's the one thing would be interesting to consider and take into account. And the second, I have a question about the your plot of the OCS as for stars of different spectral classes from GK and M dwarfs. So is that what? Because again the UV emission depends on the stellar age. So what stellar ages are you considering for GK and M dwarfs in that plot? Thank you.
Yeah, thanks for the questions. So on the comment, yes, we need to consider, escape is going to be a process which modifies atmospheres on long time scales over the course of their life. And the kind of closed box models that we presented are definitely, just a kind of an M-member case. They're kind of useful to understand in their own right, and they need then other processes like escape layering onto them to be, a plausible description of a given planet. So I think that's a really good point. In terms of the spectra used in Sean's paper modeling the exovenuses, that's a really good question. So the spectra were taken from the Muscles database, if I remember correctly. So I think what I'm going to do is just point you towards kind of a bit of a cop-out, but the spectra used are actually plotted in Sean's paper. Figure 2 of the paper contain a plot of all the spectra. So I think that's going to be the best place to go to get the right answer rather than me trying to remember now. But yeah, the paper's published in 2021 in AppJ, and if you get a chance to look at that and have any more questions, please do email us, or suggestions about spectra we should reperform the calculations with.
Thank you.
Thank you.
We have a question from Debjit Pathak in the chat, who asks, how will iron delivery to a growing planet by pebble accretion be geochemically any different from the impact scenarios?
Yeah, so that is an interesting question. So I'm going to assume to answer the question, I'm going to assume like an all else being equal scenario. So like let's imagine that a planet accreted a certain mass of stuff, as late accretion, so after core closure, and after it had a solid surface. How significant would it be basically if that stuff arrived as small objects versus large objects? So I think the answer to that is it would matter a lot. So in the case of large objects, as kind of saw in some of those figures and that simulation I showed actually as well, like a large impactor impacts the surface, driving melting and throwing material from the system altogether, and also embedding material deep into the interior of the planet. So all of those things are only possible because it's a large impactor and imparting very significant energy. If that mass was distributed among small objects, then any one of those objects is not going to melt the surface, is not going to eject debris from the system, and is not going to implant material deep into the interior of the planet. The result of which is going to be all of that added mass is going to be a vapor interaction with the atmosphere. So that would be a really big difference. So it will matter a lot what the size distribution of the late accreting material is, and whether it's kind of highly stochastic and large objects, or lots of small objects, in which case there's less stochasticity. So I think that's a good question. Yeah, and points to an important variable when considering the potential early atmospheres planets may have as a result of these kind of accretionary processes.
Well, if there are no other questions, we'll thank Ali very much for coming to give the talk today, and stay tuned for further announcements on future Clever Planets talks. Thank you.